For set operations, you need a definition, and the first definition that you need is what is the universal set. U for universal set is the set that contains everything relevant in the discussions. But as a class note, we could write it like all elements. But if you read the textbook, they say relevant to the discussion, because my universal set could be all numbers from 1 to 10 in problem 1, and my universal set could be all numbers from 1 to 100 in problem 2, for example. So what we call universal is arbitrary. That's what is relevant to the discussion. Then we have a set A. Let's have a set A, or B or C. All elements, all sets are a subset of the universal set. So if you have sets A, B, and C, by definition, that U contains all elements, then A is a subset of U, B is a subset of U, C is a subset of U, etc. Obviously, the empty set is always a subset of any set, so this applies to. So that's the first point. Then we have the definition of complement of set A. You put a bar over here, asterisk, and that means complement of set A. I like to call it not A. What is the complement of set A? Is all elements in U which are not elements in A. That's why I like to call it not A. Not A, because it's an element that is not an element of A, and you got A bar. For example, if my universe is numbered from 1 to 5, and let's say A, just because I want to call it, is going to be 1 and 2, not A is going to be, or complement of A, that's the proper terminology, complement of set A, but I call it not A, are elements in elements in U that are not element is in A. So it's going to be 3, 4, and 5. That's complement of set A. What I call it not A. Proper definition: X such that X belongs to the universe, but and X does not belong to A. X is an element of the universe, the universal set, and X is not an element of A. So in colloquial language you say X is in U but not in A. Now we have the definition. We are going to go, and these are no operations, these are just definition. Universal set, I call it universe. When I'm explaining a program, I just call it universe, but it's supposed to be the universal set. And complement of set A, complement of set A, but I call it not A. And now we are going to go to the operation. So the first operation is called intersection. Intersection of sets A and B. So intersection of A and B, and the intersection of A and B is all elements such that X is an element of A and X is an element of B. That's the proper terminology, but in my language I prefer to say X is in A and also is in B. Remember that and is very restricted. Then we have the definition of union of set A union B, and A union B is the elements X is an element in A or X is an element of B, or is less restricted. And now we are going to see this as an example. For example, my universe is going to be numbered from 1 to 10. And A, I will call it the odd numbers. B, I call it the even numbers. And C is going to be, let's say, numbers that are divisible by 3. So 3, 6, and 9. Just to do a couple of examples over here. So for example, if A is the even the odd numbers and B are the even numbers, A union B is going to be the universe. Because if I say to you odd numbers or even number, that is everything. Now if I say to you A intersection B is empty, is the empty set, because a number cannot be odd and even. But if I do A intersection C, these are the numbers in A and in B, and I got 3 and 9 because 6 is even. So 3 is in A, yes. 3 is in C, yes. 3 is in A and 3 is in C. 9 is in A and 9 is in C. And you could also check for your your understanding that A intersection the universe is A. Check it out. Make a universal set and make a subset A from the universe. You're going to see this, and you're going to see that A union U is U. So the intersection with the universe is the set itself, and the union with the universe is the universe. So check it out. And you could do it the same for B. You could do the same thing for B. B intersection U equals B, and B union U is B. So this is not for A or B. This is for any set. Any set intersecting with a universal set is the set itself, and any set union with the universal set is the universal set.